I think that is everything. Don't forget you can do your seating chart. We still have a few minutes. How y'all doing? Any questions? You know what next Thursday is, right? Yeah, it's our exam, but it's only 2 chapters, so that's kind of nice. And we had 3 days on chapter 6 instead of 2 days, so that's kind of nice. But chapter 6 is really important. And like lots of things build on chapter 6, so. So yeah, get your eye clickers out. Make sure you have your eye clicker ready. We will have some eye clicker questions. I have a couple of extra jokes if y'all want to hear them today. Yeah. All right, let's see. What kind of a dinosaur likes to sleep? A Stegosaurus. Okay, I don't think I told y'all this one. Sometimes we get extras during the day. Let's see. How fast is milk? Did I tell y'all this one? It's past your eyes before you know it. I did tell you that one. Yeah. All right. Let's see. This is classic for fourth grade humor. What did one toilet say to the other toilet? You're looking very flushed today. Yeah, that's the good stuff. Right? He was quite entertained with that one. Let's see. I'm trying to see if I remember some more. I don't know. We get so many that it's so hard to keep track of. I'm glad I can tell them to y'all and then make room for the next joke of the day. All right, so just a reminder, today is Thursday. What happens next Thursday? Have an exam on which chapters? Just 6 and 7. So just 6 and 7. So, you know, it's kind of good and bad, right? But start studying. Please take the weekend and make the best of the weekend. All right. And I haven't had a chance yet. Somebody in the other class, I think it was the other section, asked me to make a video of the parts of the worksheet from last time that we didn't get to finish. So I didn't get a chance to yet, but I do plan to. So when I get that posted, I'll send out like an email to the class so that y'all know. Okay. All right. Any other questions before we start? Okie dokie. All right. So make sure you did your seating chart. And then let's do some eye clicker. All right. View full screen. Here we go. Let's make sure it's all the way on there. All right. Lactose has a blank glycosidic linkage. Remember, 1 minute. Okay. Everybody click in. Don't leave it blank. All right. You can talk to the people around you now. Go ahead. I'll give you 45 seconds to chat it out. But I think y'all got it. Okay, 10 seconds. Make sure you click in again. I thought we had 36. There we go. Okay. So what did y'all say? Good, very good. So it is A. Let's see, let's go back and do this one. All right, so how did you know it was A? What was the very first thing that you did? You found your anomeric carbon. Found your anomeric carbon. Your anomeric carbon, how did I know that this was my anomeric carbon? It's bonded to 1, 2 oxygens. There's no other carbon attached to it outside of the ring. So this must be carbon number 1. I go and do that for my other sugar molecule. I have my 1, 2 oxygens. So this must be my anomeric carbon. Is there another carbon attached outside of the ring? No, so I give it a 1. But what do I notice now? My anomeric carbon is not participating in the glycosidic bond, right? So I'm only going to have one of those alpha beta things, right? So I go 1, 2, 3, 4. So this and this one are the 2 carbons that are participating. So we have a 1 to 4, but how do we know if it's alpha or beta? You're going to look at the carbon that's outside the ring. It's going up. And I'm going to look at my glycosidic bond. It's going up, and up is. Very good. All right. Okay. Now remember when I said you had to learn your sugars? Remember that? So what is sucrose? Remember how I said learn your sugars? You do have your notes in front of you. And remember, sucrose is one of those ones that is in your cabinet at home. Ten seconds. Don't leave it blank. All right. Turn and talk to the people around you. So I'll give you 30 seconds on this one. Click in again. You can use chat. If there's a couple of people in chat, you're welcome to use the chat function. Okay, so what did we say? So it is B. All right, 100%. That is awesome. So it is a disaccharide containing fructose and glucose. So do you have to know your disaccharides? Yes. Do you have to know your polysaccharides? Yes. So make sure that you know those. Okay, why are oligosaccharides important? Okay. Don't forget to ring in. It's a minute. Ring in. Okay, so turn and talk to your neighbors. $45 seconds. So you got another 15 seconds. Okay, make sure you click in again. Don't forget to click in again. Okay, so let's go through each one. Oligosaccharides are the main structural materials in plants. True or false? False. How could I make this statement true? Polysaccharides. B, oligosaccharides are the major energy source for plants and animals. True or false? What? False. How do I correct it? Poly. And really, polysaccharides are the major energy source for plants, period, right? Our major energy source is things that we eat, right? So it's not one particular type of sugar, right? It's everything that we eat. So what are the polysaccharides that are the major energy source for plants? Like when the sun goes down, what's the major source of energy for plants? Starch, right? Starch. And starch is what two? Polysaccharides. Amylose and amylopectin. Okay. C, oligosaccharides are a form of energy storage for animals. True or false? False. How do I correct it? Poly. What is energy storage for animals? Which polysaccharide? Glycogen. Glycogen. All right, oligosaccharides on cell surfaces allow immune cells to distinguish a person's cells from the cells of another organism. True or false? True. What is the definition of an oligosaccharide? 3 to 9. It is 3 to 9. Poly is 10 or more, right? So how many, if you're a type O person, how many saccharide units do you have in your oligosaccharide? 3. If you're type A, how many do you have? 4. If you're type B, how many do you have? 4. So they're all 3 are oligosaccharides. Okay. All right, let's try another one. I think this is the last one. Yeah. Select the false statement. Be careful, you're selecting a false statement. One minute. Please make sure those masks are over noses and mouths. Okay, 10 seconds. Sure you click in with something. Okay. Talk to the people around you. You can check in again. That was quick. I'll give you till 30 seconds on this one. So everybody make sure you check in by 30 seconds. Put your second answer in. I think y'all know the answer to this one. Yeah, y'all got this. Okay, 5, 4, 3, 2, 1. All right, so is A true or false? True, because type O blood is the universal donor. So can type A be the universal donor? No, let's fix this. Individuals with type A blood can donate blood to A and who else? AB, themselves and anything more than them. Individuals with AB can accept blood from anyone. True or false? True. AB is the universal recipient. Okay. Type A blood has type A markers. Yes. Type AB blood has A and B markers. That is correct. Okay, so it should have been B. Good. And good. Very good. All right. Okay, so let's now go on to chapter 7. Okay. So we're going to talk about all the different kinds of attractive forces that are involved in first gases, then solids and liquids, how that affects solubility and how that affects things inside of a cell. So it's kind of a complicated and diverse chapter in this one. But we're going to start with gases. And when we talk about gases, you're going to have to convert between units for a lot of different things. One of those things is pressure. So you'll see lots of different units for pressure. You will see ATM. What does ATM stand for? Look at the top. Atmospheres of pressure. What is PSI? Pounds per square inch. Like that's what you measure on your tires, right? Pounds per square inch. Millimeters of mercury. That one's kind of weird, right? So what is that? You can take a dish and you can fill it with mercury, but don't do this. Don't handle mercury, but you can. And you put basically like a test tube upside down on the dish. And because there are air particles, those air particles are going to collide with the surface of the mercury. And it's actually going to force the mercury up into the tube. And however much pressure that atmosphere is inducing on that mercury will tell you how high up the mercury goes. So at sea level, at 1 ATM, it's going to go up 760 millimeters mercury. So the more pressure, the higher it will go. The less pressure, the lower it will go. It was just an old-time way to measure pressure. And then pascals, right? So I put those up at the top, but where could you find these things? In your best friend. So your best friend, if you look, there's a section on pressure, and it shows you all of these. And it says 1 ATM is equal to all these different things. So use it, have it out right now. So the first thing we're going to do is just some practice conversions, because you'll have to do this. So convert the following barometric pressure readings to ATM. So we have 101,331 pascals. Whatever we have on top and we want to get rid of, we put it on the bottom. Where are we trying to go? We want to convert the following barometric pressure readings to ATM. So where do we want to go? ATM. Do we have a conversion factor that links ATM and pascals? Yes? It's 1 ATM is equal to how many pascals? 101,325. So my pascals will cancel. And what do I get? Really close to 1, right? The two numbers are very close to one another. One's in the numerator, one's in the denominator. What do you get? Technically, how many significant figures should you give me? Let me ask you this. Technically 6, because we don't include conversion factors when we are determining number of sig figs. So I'm not really looking for 6, just give me the 3. I don't really want 6. So what's my answer? 1 ATM, right? Okay, how about B? We have 762 millimeters mercury. Do I have a conversion factor between millimeters mercury and ATM? Yes. 1 ATM is how many millimeters mercury? 760. 760, so 762 divided by 760 is about 1, right? 1 ATM, because my millimeters mercury canceled. How about C? 14.6 PSI. I'm going to put PSI on the bottom. I want ATM. My conversion is 1 ATM is equal to how many PSI? 14.7. 14.6 divided by 14.7. It's not quite 1. It's actually like 0.99, right? But basically it's 1. 0.99, it doesn't round up, does it? What is it? 0.993. You're given 3 sig figs. Okay. All right, so before we go on to the next problem, I want to give you a little way to succeed for this section, right? There are 2 things that you need to remember in order to be able to do all the gas stuff. Okay, one of them is called the ideal gas law. The ideal gas law says pressure times volume is equal to number of moles times a constant times temperature. You will never actually have to plug into this formula. You're just going to use this conceptually. So go ahead and write down what the different things are. This is pressure, volume, N is number of moles, R is the gas constant. So it's never going to change. It's a constant. It looks like a variable, but it's not. It's a constant. And then temperature. So let's look at this equation. You know, I call this equation PIV-NERT. All right. It's a way to easily remember the letters, PIV-NERT. So this is just algebra. If I have 2 variables, and in this case, let me talk about volume and temperature. If I have 2 variables that are on opposite sides of the equal sign, if one of the variables goes up, what happens to the variable on the opposite side of the equation? It goes up. Okay, why? Why? The left side has to equal to the right side. So if I make the left side big, what do I have to do to the right side? I have to make it big, right? Okay, now what if I have the same formula, PV is equal to nRT? What if I have something where I'm looking at 2 variables that are on the same side of the equal sign? So if one goes up, what does the other one do? It goes down because the left side has to equal to the right side. The right side has not changed. And I just made it go up because pressure went up. So what would volume do? Go down so that they can be equal again, right? So make yourself that little note. If they're on opposite sides, variables on opposite side are, we call this relationship proportional. If you have variables on the same side of an equation, they are inversely proportional. But this, you have to assume that everything else in the equation isn't going to change, right? So like if I'm looking at the bottom one, then N, R, and T can't change, right? And we'll talk about why that's important. And we'll use this. But if you remember this, you're going to be okay. It's all algebra. Okay, so that's PIV-NERT, the ideal gas law. So make sure you copy this down. I still see some people writing, so I want to make sure you get it. Yes, ma'am. Moles. It's an M. M-O-L-E-S, moles. Okay. Now, that's half of what you need to know. right? So that's PIV-NERT. The other thing that you have to know is you have to put your peas and vegetables on the table. That sounded crazy, right? So a lot of times what we do is we have a condition and we change something, and we want to know how a variable is going to change. How is, if I change temperature, how's pressure going to change, right? So what we have is our peas and our vegetables on the table equal to our peas and vegetables on the table. And one side of the equation is our initial condition, and the other side of the equation is the final condition. Now, this combines all the different gas laws that are in the textbook that you have to know. So vocabulary wise, you have to know all the gas laws. But when it comes to solving a problem, I'm telling you, every single problem I give you can either be solved with peas and vegetables on the table or PIV-NERT, one of the two. So let's talk real quick about those three different gas laws that you need to know. The first one is Boyle's law, B-O-Y-L-E-S, Boyle's law. What is Boyle's law about? You remember the little thing I told you in the video? Right? This kid was going to prom. He was going to this really big dance. And he looked in the mirror and he had this massive boil on his face. And he was just peeved. PV, peeved. So pick out P and V, right? So tell me about P and V. So this is pressure and volume. What's the relationship between pressure and volume? PI, PV equal to PF, VF. What did I do? I did my peas and vegetables on the table, right? I just didn't keep the table. Yeah? So all of your gas laws, you already know, as long as you know which two variables they have. If you know your peas and vegetables on the table, you know all the relationships. Okay, then what was our next one? Charles's law. Right? Charles's law. This is not who my Charles was named after. But this is how I remember Charles's law. When I was growing up, there were TV shows with Charles in it, like Charles in Charge and Charlie's Angels, right? So there were TV. They were on TV, T and V. So if I do peas and vegetables on the table, in order to keep T and V, what do I get rid of? P. Isn't this so easy? If you know your peas and vegetables on the table, you are fine. Okay, the last one is Gay-Lucex. ACS, I think, law. So Gay-Lucex law, you just have to remember, is pressure and temperature. So what's my relationship between pressure and temperature? Peas and vegetables on the table, peas and vegetables on the table. What do I get rid of? Volume. So initial, final. Isn't that a nice way? Yeah. I'm all about work smarter, not harder, right? So really, you have to know ideal gas law and peas and vegetables on the table. So let's go use those two. The hardest thing is going to be determining which one to use. But if you use your peas and vegetables on the table, that's when you have an initial condition and a final condition. It's a good rule of thumb. Okay, so suppose, did I do the problem at the bottom? I think I skipped one. Did I skip one? No, I didn't. Okay, sorry. Suppose you had the same amount of gas in two containers, C and D. Both containers are at the same temperature. Container C is half the size of container D. Which gas is at higher pressure? Explain. We're going to explain it two different ways. First, I want you to use what we just talked about. Are we going to use peas and vegetables on the table or PIV-NERT? Do we have an initial and a final condition? No. So what should we use? PivNert. Let's use PivNert. Okay, so it says, suppose you had the same amount. Whenever you see something that says same amount, this is telling you that you're holding something constant. What is being held constant in this problem? The amount of gas. What does amount refer to? In PivNert, one of those variables. So if you had the same amount of gas, not size of container, but amount of gas. If I tell you have 10 M&Ms, you have 12 eggs, you have 1 mole of carbon. What are N? N is our number of moles, which is N, is held constant. Okay, so we don't have to worry about N. R is a gas constant, so we don't have to worry about R. Read the next sentence. Both containers are at the same temperature. So what else is constant? Temperature. So we don't have to worry about temperature. Container C is half the size of container D. So what am I doing to volume? I am decreasing volume. If I decrease volume, what happens? Then you have an increase in pressure. Right? Okay, now I want to share a different way to think about this. So remember when we were talking about chemical reactions, and we said what makes a chemical reaction happen? And we talked about it, equating it to cars on the road. And we said when those cars collide and they collide with enough energy in the right orientation, a chemical reaction happens, right? And so we were able to talk about number of particles and the speed of those particles. I want you to go back and pull on that. So if I have, let's say, a city, right? And this city is a certain size. And then I have another city, city D, that's half the size. I put the same number of cars in city C as I do in city D. Which one is going to have more collisions? City C or city D? Whichever one is smaller, right? So if city C is half the size of city D, then city C is going to have more collisions because you have more cars on the road. Well, when we talk about gases, pressure is the number of collisions against the side of a container. So because container C is smaller, so it has a lower volume, right? But the same number of particles, then we'll have more collisions of those particles with the sides of the container. And that is the definition of pressure. And we'll have more collisions with the sides of the container, which is an increase in pressure. So that same car analogy still works. It's kind of a useful one. Now, the next time you see like a balloon, you're going to think about the little atoms of the gases driving around, right? Okay. All right. Ooh, let me hide that. So our next one, when you swim underwater, the pressure of the water pushes against your chest cavity and subsequently reduces the size of your lungs. So for every 10 meters below the water surface, the pressure exerted by the water adds 14.7 psi to atmospheric pressure. So the total pressure 10 meters below the surface is 29.4 PSI. How did they get this 29.4 PSI? How did they get that? 14 point what? 79? It's what? Oh, times 2. So this is, so what is this? PSI. This is 1 ATM, right? So if you're at sea level, just that's like us right now, right? We're basically at sea level. We are sitting at 1 ATM of pressure. 1 ATM of pressure is 14.7 PSI. Then we're going to jump into the water and we're going to swim 10 meters down. So we have the pressure from the air plus the pressure from the water. So every 10 meters below the water surface, we're going to add 14.7 PSI. So this one is the air. This one is 10 meters of water. And we get 29.4 PSI. Right? That's where they came up with that 29.4. I don't think they were very explicit in the question, right? But that's where it came from. So I'm going to erase this now because we don't really need it. I just wanted to explain where it came from. Okay. Because that's not part of our calculation yet. All right. So the question is, right, if you have a lung volume of 6 liters at sea level, which is atmospheric pressure, what would the volume of your lungs be when you were at the bottom of the pool that is 5 meters deep? First question you ask yourself when you look at this, any problem. Am I using peas and vegetables on the table or am I using Pivnerd? What do you think? Peas and vegetables on the table. Why? Because we have a change. We're going from an initial condition, we're doing something, and we're getting to a final condition. So then I want to pull the information out of the problem because that's kind of a lot of information in there, right? So I'm going to say, okay, here are my initial conditions. What do I know initially? Initial, in this case, where am I? Am I out of the water or am I in the water? I'm at sea level. So I'm not underwater. I'm standing on the dock, right? Okay, so initially at sea level, what do I know? I have a volume initial of 6 liters. So right here, this is my volume initial. What else do I know initially? So I know that I'm at atmospheric pressure, right? What is atmospheric pressure? You could say 1 ATM, or what else could you say? 14.7 PSI. Okay, so that's initial. Do we have anything else? Do we have temperature? We're assuming no temperature change. Okay, so draw a little squiggly line. Let's do final. Am I at sea level when I'm in my final condition? No. Where am I? I'm 5 meters deep. 5 meters underwater. Do I know my volume final? No, that's what would the volume of your lungs be, right? So this is my unknown. So I like to put my unknown as a little question mark. Okay, do I know my pressure final? It's not explicit in the question, is it? You have to kind of go figure it out. So let's go figure it out. Let's come down and let's go figure it out. Pressure final. Okay, so what I know about my pressure final is that it's a combination of 2 things, right? So my combination of 2 things are, I want my pressure at sea level, That's the atmosphere, right? Plus my pressure, 5 meters of water, right? Just like they did in the problem. So what is it at sea level? We know that off the bat, right? 1 atm or 14.7 psi. Okay, now in the problem, they don't tell you what the pressure is at 5 meters, but they do give you the pressure at what depth? 10 meters. So at 10 meters, we have 29.4 psi per 10 meters, right? So if I want to find my pressure at 5 meters, all I have to do is multiply by 5 meters. My meters cancel, I end up with psi. So what is this unit? So I'll end up with 14.7 psi plus what? The 29.4 times 5 divided by 10. Should be 7.34 34. What did you say? 35. 35 psi. So now add those together and you're going to get your pressure final. So what's your pressure final? 20 what? 22.05 psi. Okay. So now that I've like set up my problem, yes. Did you put this into parentheses? So if you're adding them, if you do this, it'll add 14.7 plus 29.4. It'll do the addition first.
Wait, we're adding.
So to get this, to get 7.35, so do 29.4 times 5, hit enter, then divide by 10. Anybody get 7.35? Somebody said they got 7.35. It is 5 meters times, oh, I'm doing the wrong thing. It is, that was the total. I pulled the total. Water adds 14.7 psi. So the total 10 meters below was 29.4. But for every 10 meters below the water surface, the pressure exerted by water adds 14.7 psi. I'm sorry, y'all. So this should be 14.7. Sorry about that. Thank y'all. Yeah? Okay. So we're only at 14. Yep. Okay. So now we good? Yes. Okay. So now what are we going to do? Peas and vegetables on the table or Pivner? Peas and vegetables on the table equals to peas and vegetables on the table. Do we need all the peas and vegetables in the table? No, what can we get rid of? The table. We can get rid of the table, right? As long as you do the same thing on both sides, you can do that. So now all I have to do is say, oops, say this is my pressure initial, my volume initial, my pressure final, my volume final. Okay, so my pressure initial was 14.7 psi. My volume initial is 6 liters. Pressure final is what? 22.05. My volume final is what I'm looking for. So all I have to do is divide by 22.05. Now this is why it's important to write your units. So if we did this and we had some things in ATM and some things in PSI, you would notice that the units don't cancel out. So you have to be very careful that all of your units cancel out. Okay. So VF is equal to what? For what? Liters, right? That's my only unit that's left, liters. So when you go 5 meters deep, that's not that far. You go from having 6 liters of volume in your lungs down to 4. That's a huge difference in such a short depth. Okay. Here we go. All right. A gas has a volume of 10 liters at 0 degrees Celsius. What is the final temperature of the gas in degrees Celsius if its volume increases to 25 liters? So question is, peas and vegetables or Pivner? Peas and vegetables. Peas and vegetables. So I want my initial. So my gas has a volume of, so that's volume initial of 10 liters. What else do I know? Temperature initial is what? What is it in the problem? 0 degrees Celsius. We're going to talk about that in a minute. Now my final. What do I know finally? Do I know my final volume? Volume final is 25 liters. And then temperature final is my unknown. But I want it in, what is the final temperature of the gas in degrees Celsius? So what are we using? Pivnerd or peas and vegetables? Peas and vegetables on the table. All right, peas and vegetables on the table equal to peas and vegetables on the table. Do I need to get rid of anything? Get rid of your peas. Okay, so now let's go plug things in. So this is, I'm sorry, initial, final. Okay, so what's my volume initial? 10 liters. What's my temperature initial? 0 degrees Celsius. What's my volume final? 25 liters. What is my temperature final? Is my unknown, so I'm just going to leave it that way. So what do you do to solve for temperature final? Sure, you can cross multiply. Okay, so temperature final, then you would end up with temperature final times 10 liters is equal to 25 liters times 0 degrees Celsius. What happens when you multiply by 0? Everything is 0. But there's a temperature there. It's not. That's my problem, right? All of my temperatures, when I do all of my pressure stuff, cannot be in Celsius. And this is one of the reasons, because you can't have 0 and you can't have negative. It doesn't make sense. So what we have to do is we have to convert for all gas problems. We must convert Celsius to not to Fahrenheit. Ooh, the big F. Do not. That's the F word in my book, right? Fahrenheit. You want to convert Celsius to Kelvin. Why do we use Celsius sometimes? It's really interesting to use Celsius because they set the Celsius scale so that boiling is 100 degrees Celsius and then 0 is freezing point of water, right? So it's boiling and freezing point of water being 100 and 0. So it's kind of neat like that. You can picture things, but really in calculations, you should use Kelvin. So how do I go from degrees Celsius? How do I get Kelvin? Add 273. And I think, is that on your sheet? Yes. So look at temperature. There are 3 equations. It's the 3rd equation. It's there on your sheet. So you don't have to memorize that. It's on your best friend. So this is not really 0 degrees Celsius. It is 273 Kelvin. So then take this whole thing and divide by 10 liters. Temperature final is equal to Should be pretty big. 682 Kelvin. Am I done? Nope, right, that's your key that you know you're not done. If Dr. B asks you, are you done? What do you have to do? I have to convert it back because in the problem it says, what is the final temperature in degrees Celsius? So what am I going to do? Subtract 273. So I get my temperature final in Celsius as 409, not 410. 409 Kelvin. Not Kelvin. Degrees Celsius. So like if boiling water is 100 degrees, how hot is 409 degrees Celsius? That's pretty hot. Right? That is quite warm. Quite warm. Okay. So assuming no air can move in or out, what happens to the volume of a hot air balloon as the air is heated? So what should we use to kind of answer this? What's a good peas and vegetables on the table or PIV-NERT? I like using PIV-NERT. PV is equal to nRT. So assuming no air can move in or out, what does that tell me? What is constant? So you have a constant N. So you don't have to worry about N. Do you worry about R? No, it's a constant, right? So what happens to the volume as the air is heated? What are you changing? The air is heated. Temperature. You going up or down? Up. Okay, so now what happens to volume? If they're on opposite sides of the equation, if one side goes up, the other side must go up. Right? So this is why, have you ever seen those hot air balloons, right? They have the basket and then they have the flame and then it's the balloon. And before they've taken off, the balloon is all like flopped over. It's empty, basically. You know, it's deflated. And then they turn the fire on and what happens? That balloon starts to inflate and eventually they get enough in there, enough hot air that it actually rises, right? Yeah, pretty cool. Okay. All right, here's a more practical application for you. An ambu bag. So an ambu bag is what they use to force air into people's lungs, right? So how does that work? Well, if you squeeze an ambu bag, what happens to the volume? It's like a balloon. If you squeeze it, what are you doing to the volume? You're decreasing the volume. So let's use PV is equal to nRT. If we squeeze it and we drop the volume, what happens to the pressure? Goes up because they're on the same side of the equation. They must be inversely proportional. So if the pressure goes up, how does that help a patient who's not breathing, right? If air is under high pressure, so high pressure air is actually forced into the patient's lungs. Right? And that's artificial breathing. And then what happens when, so squeezing the ambu bag is basically someone inhaling, filling their lungs. And then what happens when do you just squeeze it once and you're good? No, you have to let go of the bag so that the person can then exhale. And then you keep doing it, right? Don't stop. Don't stop. So it's actually a little bit complicated because of the valves and all kind of stuff inside of it. But it's really interesting. And I found a really cool video of how it all works. And so if you look in the chapter 7 material, like the very last video is a video about it. I thought y'all might really be interested. So, you know, I'm not testing you on it, but it's really cool. It's really interesting. Okay. So now we have an application, but it's not so practical for y'all, right? Volcano is not so much your forte. All right, so we have a 100 milliliter bubble of hot gas at 225 degrees Celsius, pretty hot, and 1.8 atmospheres that escapes from an active volcano. What is the new volume of the bubble outside of the volcano where the temperature is minus 25 degrees Celsius and the pressure is 0.8 atm? Peas and vegetables on the table or Pivnert? Peas and vegetables. Y'all are awesome. Y'all are, see how easy this is? You got two choices. Peas and vegetables or Pivnert. Okay, initial. What do we have initially? Which is my volume initial. Okay, what's my next thing? Which is 225 degrees Celsius. We don't want that, right? What do we want? Kelvin, how do we get Kelvin? 273, not 237, plus 273. Okay, so what do you get? No, add. 498. Okay, then we have pressure initial, right? So what's my pressure initial? 1.80 atm. Okay, tell me about my final conditions. We're out of room already. So do we know volume? No. That's our unknown because it says what is the new volume, okay? Where the temperature is final. It is minus 25 degrees Celsius, but we don't want that. We want plus 273. So what do we get? 248. And then we have pressure final. Our pressure final is 0.80 atm. So then we're going to put, just like y'all said, peas and vegetables on the table. What do we get rid of? Nothing. We're going to use it all. So isn't this nice? You don't really have to know which law to use. You just put them all and then get rid of what you don't need. Okay. So my pressure initial was 1.8 atm. I always put my units. Volume is 100.0 milliliters. Temperature initial is 498 Kelvin. Pressure, I did all eyes. Feeling the eyes, I guess. Okay, pressure final was 0.80 atm. Then volume final is our unknown divided by 248 Kelvin. So then what I do for this to get my volume final alone is I multiply by the inverse. So I go 248 Kelvin on top, 0.80 atm on the bottom. So that cancels with that. So then whatever you do to one side, you have to do to the other. So we had 248 Kelvin on top and 0.80 atm on bottom. So our ATMs cancel, our Kelvins cancel, we're left in milliliters. So our volume final is, I get 112 milliliters. What y'all get? Yeah. Well, so if you look at the problem, right? Really, you have two sig figs, so 110. Okay. All right. A cylinder of compressed gas empties, the pressure inside the cylinder decreases. Explain why this happens using the ideal gas law. Peas and vegetables on the table or Pivnert? This one was easy, right? It told you which one to use. Ideal gas law, Pivnert. PV is equal to nRT. Okay, so a cylinder of compressed gas empties. What does that mean? Be careful. This is a cylinder of compressed gas. So think about, you're going to get balloons for a party, right? So you have this tank and you attach the balloon to the tank and you open the valve, and what happens? It's not air, usually, well, it could be air, but a lot of times it's helium, right? So the gas goes from the cylinder into your balloon. Does the volume of the tank change? No, what changed? Number of moles, right? You actually had individual particles of helium that moved from the tank to the balloon. That's why, like, you empty the tank, right? Maybe one tank can blow up 1,000 balloons, right? Because it's compressed gas. It's under high pressure. So as we let out a little more gas and a little more gas, have you ever gone and had a balloon blown up? If the tank is really full, when they open it, how does it sound? It makes that really, really high pitched, right? But then as the tank gets less and less empty, right, it gets quieter and quieter. Why is that? Because the pressure is decreasing, right? Isn't that so cool? Okay, so a cylinder of compressed air empties. This means you reduce number of moles. The pressure inside the cylinder decreases. Explain why this happens using the ideal gas law. So as the number of moles decreases, what happens? Ooh, I added too much, right? You have, now let's talk about pressure, right? The fewer cars you have driving around in that cylinder, what happens? You have a decrease in the number of collisions of gas with the sides of the container. So pressure goes down, right? But this assumes, right? This assumes that everything else is constant. So that volume is constant, that temperature is constant. Because if you change temperature or you change volume, those things will change. So if we talk about a balloon can change volume, but a cylinder cannot. Okay. All right, so that was gases. Feel pretty confident on gases? Remember your peas and vegetables on the table and Pivnert, you're gonna be okay. Okay, now we're gonna talk about how solids and liquids interact. And they all interact through attractive forces. We have talked about attractive forces in this class before. And it had to do with water. What kind of a molecule is water? It is polar. So if I ask you to draw a water molecule, is this okay? It's a good start. What else do you need? See some people doing some dots, right? What are those dots? Lone pairs of electrons. So look at the periodic table. Where is oxygen? Oxygen is the next door neighbor to who? Fluorine the floozy, right? So fluorine is the most electronegative element on the periodic table. Oxygen is the next door neighbor. So how electronegative is oxygen? Pretty electronegative. So what does that mean for my water molecule? That oxygen and hydrogen have different electronegativity values. So what can you tell me about one of those bonds between oxygen and hydrogen? Why do I call fluorine the floozy? Why do I call her a floozy? She takes anyone's electrons. She doesn't care. So oxygen is a lot like that. Oxygen is greedy and will take most anyone's electrons. So who is oxygen taking electrons from? Hydrogen. So when oxygen takes electrons from hydrogen, what do we say about this bond? It's a polar bond, correct? Yes, we've talked about this, right? I remember this. So you have two polar bonds. Because you have polar bonds, that results in the hydrogen becoming partially positive, the oxygen becoming partially, Dr. B, negative. The other hydrogen is partially positive. Okay. This is what makes water amazing, because each of the bonds is polar and the molecule is asymmetric. Every water molecule is going to want to interact with every other water molecule, right? So if I have a partially positive hydrogen here, and I had another water molecule, what part of this water molecule is going to want to interact? Yes. So this oxygen is partially negative. This hydrogen is partially positive. This one's partially positive. So I have a partial positive and a partial negative hanging out. That's an attraction, right? That is why water is awesome. Okay, so this does not exist in every molecule, right? Because we said not all molecules have polar bonds, and not all molecules are polar. Even if you have polar bonds, sometimes your shape is symmetric, and so your molecule ends up being nonpolar, right? You might have a polar bond, but you have a nonpolar molecule. So this kind of interaction does not exist in all molecules, but there is a type of attractive force that exists in all molecules. What is it? You watched the video, right? London dispersion forces. This is what we call, so what do we call over here? If I were to draw one line that points to the negative side of the molecule and the other side of the line points to the positive sign, I say this is the dipole moment. Yes? So water has a dipole. Its oxygen is partially negative, its hydrogens are partially positive, right? So that's a permanent dipole. So this water is a permanent, that is not how it's spelled permanent, in AT, permanent, y'all know what I mean, dipole. It never goes away, permanent. But you can have what are called London dispersion forces, and London dispersion forces are temporary dipoles. And when I say temporary, I mean instantaneously they will change. So how does that work, right? Every single atom has a nucleus, right? And then it has electrons. Where are those electrons? In the electron cloud. So we basically kind of say, okay, there's some space here, and the electron is just zooming around, right? We don't know its path. We can only like take a picture and say, oh, it was there. Oh, it was there, right? And so every time we say it's there, if we put a dot, we'll make basically a cloud around the nucleus. And we say this is the electron cloud. Electron cloud, right? So you have in molecules, you have lots of atoms that make up a molecule, right? So here's a molecule that has, for example, 3 atoms in it. X is an atom, right? Every atom has electrons around it. And so their clouds kind of overlap. So I'm drawing all of their clouds together. If this molecule hits a wall, what's actually going to happen? Those electrons are going to hit the wall and kind of bounce back. So here's the wall, and now I have an electron dense region, lots of electrons, and then I have an area over here that has no electrons. So it's electron poor. What do we call an area that is electron poor? Positive. What do we call an area that is electron rich? Negative. Oh my God, I have a molecule that has a dipole. I have a dipole moment. But an instant later, those electrons will rearrange and look like the original again. So it's a temporary dipole moment where you have a clustering of electrons, right? Let me ask you this. If I went and touched the wall, is the wall solid? It's actually not. In every single atom, the majority of the space of the atom, like an atom is this big, right? This is the radius of the atom. The nucleus is teeny tiny, right? And we got a couple of electrons spinning around in this great big atom. Most of this atom is empty space. So when I touch something that is solid, it's actually my electrons repelling against their electrons. Because you and everything around you in the entire universe is mostly empty space. And those electrons can move in that space. Isn't that so cool? It's like something to ponder. You're mostly empty space. It's cool. Okay. All right. Okay, so now we said you can have all kinds of different interactions that hold molecules together. London dispersion, everybody has. So if you're a nonpolar molecule, the only force you have is London dispersion forces. What if you're water? Do you have London dispersion forces? Yes, you do, because you're a molecule. Every molecule has London dispersion. So water has London dispersion, and it has what? It has another attractive force, right? The positives and the negatives that we drew up here. This interaction right here between my negatively charged oxygen and my partially positively charged hydrogen, that's an actual intermolecular force. And we call that hydrogen bonding. So if we come down, right, what is hydrogen bonding? It's an attractive force. It is the strongest type of dipole-dipole interaction. Why do we call it a dipole-dipole interaction? What did I draw in this water molecule? A permanent dipole. Well, guess what? This molecule up here also has a permanent dipole. So it's a dipole-dipole interaction. And it's really strong because oxygen is really electronegative. So we give it a special name. We call it hydrogen bonding. Is it a bond? No, it's an attractive force. I could shake. Y'all know I'm really nice. But I could just shake the person who named hydrogen bonding, because it's not bonding. It's an attractive force, but it is not a bond. Okay? All right. So we come down. What is a hydrogen bond? Water is not the only thing that can make a hydrogen bond. A hydrogen bond requires a couple of things. It requires one atom, right, that is electronegative. So look at the periodic table. Fluorine the floozy, right? She is super, super electronegative. So examples of atoms that could participate in hydrogen bonding are a fluorine atom. Who's the fluorine's next door neighbor? Oxygen, pretty electronegative. Who's oxygen's next door neighbor? Nitrogen. But I like to write it NOF, so I can say it's no fun. Hydrogen bonding is no fun, right? So you can remember which elements, right? So I just write it in a different order. Okay, so we have this one electronegative atom, and this electronegative atom has lone pairs, or one lone pair or pairs, either way. So this electronegative atom is a hog. They just want those electrons, right? I call fluorine the floozy because she takes electrons from anybody. Same thing with oxygen, same thing with nitrogen. They just want those electrons. So whenever we have this, we're going to have, let's say here, a water molecule here, and put the lone pairs, and then another water molecule here. So remind me of the charges. Water is partially negative, hydrogen is partially positive. So my hydrogen bond occurs between, and usually they don't do it as a line, usually they do it as a dashed line. My hydrogen bond occurs between my partially negative oxygen and my partially positive water. So the one that is negative is called the hydrogen bond. So the blue one is the H bond acceptor because it accepts the hydrogen. And then the partially positive hydrogen water molecule is called the hydrogen bond donor. So the red one is the donor molecule, the blue one is the acceptor molecule. Okay, so when we look at this, you're always going to have to be able to identify which one is which. And you'll have to be able to look at molecules and say, is a hydrogen bond happening in these molecules or not? So if we read the question, given that only polar molecules can participate as donors, only polar molecules can be donors, is it true that all polar molecules can be hydrogen bond donors? So it's a little complicated. What do you think? If I'm polar, does that mean I have a hydrogen? No, not necessarily. You can have molecules made up of all different atoms, right? But in order to be a hydrogen bond donor, I have to have a hydrogen that is bound to an electronegative atom. So no, right? And we'll come down here. No, H bond donor H bond donor must have a hydrogen bound to, covalently bound to an electronegative atom. And what are my three? No fun. So maybe you have a hydrogen, but it's not bound to nitrogen, oxygen, or fluorine. Or maybe you don't have any hydrogens, right? There are lots of possibilities there. All right. So considering your answers, right? Can water and carbon dioxide form a hydrogen bond? Do not answer right away. Draw it. Draw both water and carbon dioxide. So carbon has 4 valence electrons. It's going to make 4 bonds, but you only have 2 oxygens. So what does that mean you're going to have? Double bonds. Now all you have to do is figure out how many lone electrons are on oxygen. Oxygen has 6 valence electrons. 2 of them are participating in the bond. So how many you got left? 4. 1, 2, 3, 4. Now let me ask you something. Do you have polar molecules? do you have polar bonds? Yes, you have polar bonds, right? We're going to point to the electronegative atom. Yes, we have polar bonds, but those two arrows cancel each other out. So we have a nonpolar molecule with polar bonds. So this is a nonpolar molecule with polar bonds. Now let's draw water. If my oxygen over here is partially negative, that's what that means. Carbon's partially positive, oxygen's partially negative. It's going to interact with a water molecule. Here's my water molecule. Hydrogen, oxygen, hydrogen. 1, 2, 3, 4. We've got polarity going that way, polarity going that way to give us an overall of this one, right? So we have a dipole. We have a partially positive hydrogen, partially positive hydrogen, partially negative oxygen. Can they form a hydrogen bond? Sure, they could absolutely form a bond here. So yes, the donor has to be the one that's polar. So yes, they can. So you can say, yes, the oxygens in CO2 can act as what? As acceptors or donors? As acceptors of the hydrogen bond, while the hydrogens of water act as H bond donors. Yeah? Okay, that's it for today. I hope you have a great rest of your day, great weekend. Study, study, study. Anybody on Zoom need anything? Good, awesome. I'm going to go ahead and end the Zoom.